Welcome to the next lecture. Today we will start an important topic, which is actually a separate field of science and separate subject in itself called information theory. Sorry. The reason for uh, teaching this particular topic in the beginning, there are several reasons for it. Why I'm giving the justification, because you might have, if you might see some other courses or same subject taught by other people, some of them even don't teach it, or even some of them will put it at the end, which is not correct, completely not correct in my opinion. Information theory, first of all, there should not be any confusion about what information theory is. Some of you might be from other background. They might be from computer science background, electrical background. They might think that it is something related to communication systems. So let me first of all clear the confusion that information theory is not a subfield of communication system. Communication system theory. Okay. It is a separate, independent branch of mathematics. Okay, and it has applications, which has applications in yes, of course, communication systems, computer science, physics, statistics, economics, and more. There are books written on information theory, its application is in biology, its application in various subjects, but we will not go into that. And yes, we can say in one way that it is a, you can say, branch of probability theory. There is no doubt in that. Because you will see that information theory uses the language of probability theory. Now, let me motivate with some examples. What are the two fundamental problems in information theory? For that, I will give a very simple example. Let me give first example of coin tossing. Suppose you toss a coin, as usual, head or tail are the outcomes, and you map them to suppose 0 1, head to 0 and tail to 1. So you denote that by a random variable x. Okay, s of omega from this sample space to 0 1 mapping. Okay, now we would like to represent, we would like to give a representation. Suppose you have so here's a person A. Okay, he tosses a coin and he wants to convey the result to person B. Okay, and the rule is you have to convey only using binary bits 0 or 1. So here I think, and one more thing is, the probability of head, that is x is equal to 0, is same as the probability of tail, x is equal to 1, is half. Okay, very simple example. So a fair coin. Now if you think empirically how many bits at least you need, so definitely there is no other option. You need one bit. You need one bit to convey the information, right? Or we can say to represent the result, or to represent the result. Trivial example, Now at least one bit means that you can use more than one bits also. Suppose you can use 0 0 for head, and you can use suppose 1 1 for tail. No one can stop you from doing that. But here you are wasting one bit, right? Because you are using 2 bits, but one bit will work sufficiently here. Now this example may not be so intuitive because there is only one bit needed. Now let me take another example. Let's have this wheel, that casino wheel, 3 4 5 6 7 8. Suppose it stops at 8 numbers only, equally likely. So if we represent the outcome of this wheel by x, so this x can take values 1 2 up to 8. And what is the probability that x takes any value I? That is 1 by 8, right? For I is equal to 1 to 8. Now suppose again the same issue. You are here in the casino, friend A, and you are allowed to communicate with your friend B only via binary zeros or ones. Now how many bits you need at least to convey the information, to convey the result, to represent the result, right? So there are 8 possible outcomes, so you need 3 bits, right? Suppose 0 0 0 0 0 1 to 1 1 1. Okay, so this may be mapped to 1, this to 2, and this to 8. Nice. Now if you use less than 3 bits on an average, suppose you use only 2 bits, so what will happen? So you can have 0 0 0 1 1 0 1 1. So this will be mapped to 1, this to 2, this to 3, this to 4. After that you have to repeat 0 0 0 1 1 0 1 1. So this will be mapped to 5 6 7 8. So there will be definitely an error at the receiver. Suppose you are conveying your friend that I got 1 0. So he will be confused whether you got 3 or it might be 6. So there will be an error. You cannot even avoid this error. This is such a great error that the receiver will definitely make error. So it seems that less than 3 bits will not work. Okay. Now we know that the probability of getting any number is 1 by 8. Now how can we quantify this quantity, that is the minimum number of bits required to represent the outcome of a random source? So you can think of this wheel as a source of random bits or random numbers. So every time you roll the wheel, whatever you get, you put that in the binary form continuously. So when you see at the output, suppose you get first of all 3, which can be maybe 0 1 0, then you get 1, which will be 0 0 0, then you get 2, which will be 0 0 1. So if you will write the result in zeros and ones, what you will see coming out of this experiment is these bits coming out of this experiment, 3 at a time. So you can think of this as a binary source. In fact, random binary source, because every time you roll the wheel, you don't know what will be the outcome, right? And we need, so with this toy example we got, okay, we need 3 bits at least to represent, but can we have a general answer? Okay, for this we have to set the notion of information. We want to quantify it. Now here are some motivational examples. See, information, when we say information, it is related to uncertainty. right? See, if I tell you that tomorrow is Sunday, with this, do you feel any new? Do you feel with your perception that you got any information? You say no. Why? Because it's a certain event. Okay. Similarly, if I will, suppose I may use this, that tomorrow temperature will be, say 100 degrees Celsius, right? Again, you will be, heavily. So there are here two states. So this is an impossible event. This is an impossible event. So in one sense, you will be highly surprised, right? Highly. So there will be a metric. There should be a metric which, if we feel that probability of this event, it is actually, this probability of this event is 0. So we should somewhat get something closer to infinity. So you are infinitely surprised with this news, right? Whereas here the probability that tomorrow Sunday is 1, so you should get an answer closer to 0. Something is very certain, you should have no information about it. I mean, you will get no information about this thing because it is uncertain. So here was developed the notion of information. So first of all, uncertainty, if the more the uncertainty, we feel more information. Okay. And uncertainty is, now we have to see whether it is proportional to probability of an event or it is inversely proportional to probability of an event, right? Now if you see, if an event has less probability, you are more uncertain about it. So inversely proportionality means that carries more meaning. That is correct actually. So in other words, we can say that information, it should be inversely proportional to the probability of an event. But what we need is that if probability is 1, this notion of information should give answer 0, right? Also, if probability is 0, so in one sense I should be highly surprised that I should get some answer like infinity. The other thing which is a little bit philosophical in its nature, that is whether information is additive or it is multiplicative. Okay, so if I tell you about two things, does this information get added up in your mind or it gets multiplied? Okay, so in other words, when two events will happen, suppose we have event A about that tomorrow it may rain, and event B may be that tomorrow it may be, suppose, lockdown. Suppose rain has probability P1 and lockdown has probability P2. Now when I tell you these two things, first of all, what is the probability that tomorrow it will be raining and there will be lockdown, right? You know the joint probability. So if I tell you probability it will rain and there will be lockdown, since they are independent also, so it will be P1 P2. So probabilities are getting multiplied, but information should get added up. That the information about rain and the information about lockdown, in your mind in your perception, you will add up the information. There is no meaning of multiplying the information. That will distort the information actually. Okay, it's a little bit philosophical. So what I mean is, if we have some function for information, definitely we got one point that it should be inversely proportional to p. Further, I of 1 should be 0 and I of 0 should be infinity, and I of p1 p2 should be I of p1 plus I of p2. What does it mean? So here is a joint event which has taken place, and their information should get added up. Simple. Now can you think of a function which will satisfy such properties? Okay, so let's see. Suppose I of p I of 1 should be equal to 0. So we can think of lot of ways. So what can be I of p? And at the same time, I of p has to be inversely proportional to p. Okay, so what are the different options you can think of? So any guesses? So I can think of, suppose, e to the power minus, say, p minus 1. But again, no. Or maybe if I write 1 minus this. Okay, so for p is equal to 1, right? For p is equal to 1, it becomes 0. But then will it satisfy I of 0 to be infinity? No. So you can try a lot of functions. The only function, here is a word, the only function which satisfies such properties is log function. Okay, we'll take here log to the base 2 because we are dealing with binary things. So if I define I of p as, since it has to be inversely proportional to p, I will write log of 1 by p. Okay, now let's check. I of 1 is 0 and I of 0, it goes to infinity, right? Because log of 1 by p is minus log p and log 0 is minus infinity, right? You have to remember the graph of the log. So here is the minus infinity, this is p, this is log of p, and more importantly, log of p1 p2, I of p1 p2 is log of 1 over p1 p2, which will be log of 1 over p1 plus log of 1 over p2, which will be I of p1 plus I of p2. Okay, so this quantity, this is called, also in the literature, it is called self-information. Self-information gives you the notion of information for one particular outcome, right? So it means that, suppose if you take the example of head and tail, probability of head is half. Now how much information it is needed? So it will be I of half, which will be log of 2 to the base 2, which is 1 bit. Now you already knew it that it needs 1 bit for conveying the information about one outcome. Okay, now you take the example of that casino. Let me go back there. Where was the example? Okay, here. Yes, so what will be the self information here? So it's 1 by 8 probability, so self information will be I of 1 by 8 for any outcome. So it will be log of 8 to the base 2, which is 3 bits, exactly the same answer, right, which you got with the intuition. Now this is the self information. Now what will be the average, self information represents number of bits also, so average information, or also you can say average uncertainty. Okay, so for that you need to take expectation as usual. So see what you can think of. I will tell you, suppose x is a random variable now, which can take these values, suppose x0, x1, xk minus 1. Okay, these are different k values it can take, and with probabilities given by probability, x is equal to, suppose, xk, I represent by pk, k is equal to 0 to k minus 1. So to make it more clear, as in coin tossing, this k was 2, right? So you have two outcomes, x0, x1, where x0 was mapped 0, this was 1, right? And their p0 is half and p1 is half. Similarly, the wheel example, you have k is equal to 8, right? So you have the outcomes x0 to x7. So this is the general representation. Now I will have a notation that the self information I write as I of, for a particular case, suppose it is I of pk, or I can also write as I of xk, right, which is log of 1 over pk. Now this is for any particular k is equal to 1 to k minus 1, right? Now what will be the average of this self information? So average will be expected value of this self information I of pk. What is expected value? It is a discrete case here, so it will be summation, right, the probability with which the event happens times this value of self information, right? Simple. We have done this expected value, right? So this will be this quantity which gives the average information, average value of the information. This is called entropy, represented by h of x. This is called entropy. And even this is very important. This is actually the first information theoretic quantity which we have defined today. Entropy of a random, you can say random process also, but here we will use random variable x, which can take values x0 to xk minus 1 with probabilities p0 to pk minus 1 is given by notation is h of x. This is the notation, and this means is defined as summation k is equal to 0 to k minus 1 pk log to the base 2 pk, 1 by pk, right? So log of 1 by a is minus log of a, so I can also write as minus I like this weight more. It is easy to handle in this form. Okay, so now you can repeat and you can compute the average expectation, entropy You can compute the average, you compute the entropy for the cases we did coin tossing. So h of x is summation k is equal to 0 to 1, right? Pk log pk, base is 2, which is minus half log of half minus half log of half, which will be 1. Just check it, 1 bit. Okay, similarly you can take any other examples and you can compute the entropy in particular. So coin tossing, if I generalize, suppose probability of head, which is probability that x is equal to 0, suppose that is p, and probability of tail, which is probability x is equal to 1, that is 1 minus p. So this random variable, which can take two values with only two values, is called Bernoulli random variable. Okay, I will be giving examples of random variables as we need in the course. And what is the general entropy for this, right? See, you have here in the notion, you have here x0 and x1, and you have here probabilities p0 and p1, right? And x0 is 0, x1 is 1, p0 is p, and p1 is 1 minus p. So entropy is minus summation, right? K is equal to 0 to 1 pk log of pk to the base 2, which is minus p0 log to the base 2 p0 minus p1 log to the base 2 p1, and which is minus p log p minus 1 minus p log 1 minus p, right? So this particular entropy is only a function of the p. We denote it by small h of p, okay, and it's called binary entropy. It is mentioned separately because it has some interesting properties which provide some insights. So first of all, let's plot this binary entropy. Okay, we will plot it. So what we first of all find is h of 0. Now here is an important assumption. See, what will be the entropy at point 0? So when you will put h of 0, you will get a term log 0 log 0. What is 0 log 0? Okay, see, this is a problematic because log 0 is minus infinity, right? And 0 into minus infinity is not defined, right? So we will use the limiting case. Actually, what will be the limit x goes to 0, x log x, right? So this limit, how to get some idea of it? See, if you see the log x, suppose you have a quantity 10 to the power 10. When you apply log to it, it kills down the power, it brings it down, it becomes 10, right? So log to the base 10. So log kills the rate. Log, if x is linear, log x is called sublinear, right? If x has a term like square, when you put log on it, it becomes 2 log x. So log kills down the rate. Now here we are having two numbers. One is x moving to 0, right? And then there is a log x, it is moving to minus infinity. But as we know that log x is very slow, right? So here is a race between something moving to 0, something moving to infinity. It is just like a dummy example that we have some object here, suppose, and it is tied with a rope by this person A and B, and person A is more strong, right, and person B is weak. So it will this object will move ultimately in the direction of A. Similarly, this limit will move in direction of x goes to 0, and it will be 0. So limit of this is 0. Okay, so hence we define 0 log 0 as 0. It is not equal to 0. We define it to be 0 to remove the discontinuity. So hence wherever 0 log 0 appears, that is defined to be 0. Now with this we can get h of 0 is 0 and h of 1 is also 0. You can put in here 1, so it is 1 log 1, which is 0. Then 1 minus p is 0, 0 log 0 is 0. So h of 0 is 0, h of 1 is 0. Now what about its nature? So we have to find differential of this. So del h upon del p. Okay, so when you will differentiate it, what you will get? So you get p. So here is this minus 1. Then you have to differentiate the log minus log p. Then you have 1 minus p. So that will again become let me go here first. So it is 1 minus p log of to the base 2 1 minus p. So you will get here 1 minus p will go, and internal, so it will be plus 1. So plus 1, and then log of 1 minus p, right? So I think it should be here plus, yeah. Now you put this equal to 0. Okay, you put this equal to 0. Okay, so this we put 0, so we get log of 1 minus p equal to log of p is equal to half. Just check some sign change may be there. So p is equal to half, and you can also check that you can also confirm it. What will be the second derivative is an exercise for you. Check it, and what you will observe is that second derivative at p is equal to half is less than 0. So it means p is equal to half is point of maximum. So this function is 0 at 0, it is 0 at 1, and it has a peak at half. And definitely, since there is a logarithm in it, so I will plot it here. I don't have a space. So 0 1, and this is the half point. At half, h of half is 1. This type of function is called concave function, which has a maximum. So this example will give us some idea about the nature of entropy. So this much for today. So in next lecture we will again recap these basic concepts, and we will introduce other important quantities of information theory which will be needed in our subsequent lectures, and they will be otherwise useful to other communities in different directions, like computer science community also. Thanks for watching.